Welcome to video 8.2.2, where we're going to start talking about binding energy. So, before we talk about binding energy, we'll talk about Coulomb's law. And Coulomb's law states that the strength of interactions between any two charged particles, Q1 and Q2, is directly related to their electric charges and inversely related to the distance between them. So that means the strength of their charges, the higher the strength of the opposite charges, the more they'll be attracted, and then the farther they move away from each other, that attraction quickly drops off, thanks to that squared term there. K is a constant, Q is the charge, and D is the distance. Now, the binding energy of an electron is the energy required to remove an electron from an atom, and it describes how strongly an electron is attracted to the nucleus. According to Coulomb's law, an electron has a larger binding energy when it's closer to the nucleus, and that's because, the nucleus is positive, electrons are negative. The closer they are, they can act as Q1 and Q2, the more attraction there is. And when the nucleus has more protons, so if the nucleus is more positive, the overall, the word's escaping me. The overall intensity of the positive charge will be higher if you have more protons there, so they'll be more attracted. Now, according to Coulomb's law, like we said, the electron has a larger binding energy when it's closer to the nucleus and when the nucleus has more protons. So we're going to go ahead and use those definitions to look at photoelectron spectroscopy. Now, photoelectron spectroscopy, or PES for short, is a technique to determine the binding energies of the electrons in an atom. So in PES, high-energy photons or X-rays of all different energies bombard a sample of an element, and it ejects the electrons from the sample. The ejected electrons will leave with some kinetic energy, and we can measure that kinetic energy. So the energy of a photon equals its binding energy plus kinetic energy. So we can rearrange that to get binding energy equals the energy of a photon, which we know, and we put that in for those X-rays, minus the kinetic energy. And that's our binding energy. And the kinetic energy we can measure on some sensors. Now, the binding energy of each electron then can be calculated, and an electron with a stronger binding energy will move with less kinetic energy, because it used up a bunch of that energy to break the binding energy. Okay, so let's take a look at what this means and why we would care about it. So if we look at magnesium, Z equals 12, so it's the 12th on its atomic number is 12. The PES spectrum for magnesium is shown here. Right, the long-form electron configuration for magnesium. So if we look at magnesium, Mg12, know that it's right here on the periodic table, and I want you to just take a second and see if you can write the long-form configuration of magnesium on your own, and then come back and check your work. All right, the long form for magnesium is 1s2, 2s2, 2p6, 3s2. All right, so that's our long form electron configuration. Now, according to what we learned above about binding energy, which subshell has the most, the electrons that are the most tightly held to the nucleus? So you're going to think about that, then think about what the binding energy is, and try to choose answers for 1, 2, 3, 4 of these choices here. If you want to just keep them in your head, that's okay. Pause, think about it, and then come back. All right, here we go. Let's check your work. So the 1s subshell has electrons the most tightly held to the nucleus, and that's because it's closest, right? So according to Coulomb's law, the closer they are, the greater the attraction. So that means since they're more tightly held to the nucleus, these electrons are going to require more energy to remove because they're attracted more. So their binding energy is greater. That means they're going to have I kind of gave this one away, higher binding energy. And they're going to leave with less kinetic energy. Binding energy and the kinetic energy, they're kind of inverses of each other. Okay, so now let's start to take a look at this graph. So, what do the x-axis and the y-axis of the spectrum represent? Well, the x-axis is right across the bottom here. We could just read it. That's the binding energy. And that means that our binding energy, the more tightly held electrons are going to be to the left here. So if we look at our binding energy, this is kind of an inverse. So this is 1, 10, 100. So that means if there's more binding energy, they're going to be more tightly held over here with a bigger number to the left. So it's the opposite of a lot of different graphs that you'll see. And you can think about the nucleus as being right over here. So the more tightly bound electrons are to the left over here. Okay, so what's the y-axis? The y-axis is the intensity, right? So that's our intensity. And what that means is if we have more electrons with the exact same energy, that's going to be additive because they're in the same subshell, and so the peak is going to be higher. So we can compare the height of the peak, and that's going to tell us how many electrons are in that subshell. So if more electrons have the same energy, because they're in the same subshell, the peak will be higher. Okay, so why are there 4 peaks in the spectrum of magnesium? So think about that, and then come back and check your work. Okay, the answer for that one is, it has 4 peaks because, well, there's 4 orbitals, the 1s, 2s, 2p, and 3s. So magnesium has 4 orbitals. So these are the 1s, 2s, 2p, and 3s. Okay, so why is the 3rd peak over here triple the intensity of the others? So think about that, and then come check your work. Okay, so if you said that there are 3 times as many electrons in that subshell than the others, you would be correct. So there are, because it's 3 times as high, 3 times as many electrons. There are 3 times as many electrons in that atomic orbital. Okay, and then the last step, label the peaks using the subshell notation in your full electron configuration for magnesium. Okay, so let's go back up here. So the 1s2, well, it's going to be right here, so we'll do 1s. This is our 1s. And this is going to be our 2s. This is going to be our 2p, our 3s. So this has 2 electrons, 2 electrons, 6 electrons, and 2 electrons. And then we would be done with that problem. Okay, so let's take a look at the next example. So which element is represented by this PEZ spectrum? So let's go ahead and look at the peaks. So again, this is going to be my 1s peak. This is going to be my 2s peak. This is going to be my 2p peak. Alright, so that means I have 1s2, so I know that one's going to be filled because there are ones after it. 2s, 2 electrons in there. And then in my 2p peak, I notice that my 2p peak is 1.5 times as tall as my 2s. So 1.5 times 2 would be 3, so I have 3 electrons there. So overall, I have 2, 4, 7 electrons. So that means I have 7 electrons. And so if I look on my periodic table, my protons and my electrons are going to match up, and I know that Z equals 7, so that's going to be nitrogen. So this is nitrogen. Okay, example 5. Consider the PEZ spectra for hydrogen and helium plotted on the same axis. That means that one of these is hydrogen, one of these is helium. They're 2 different elements. Label the peaks as H, or hydrogen, 1s, and helium, He, 1s. How did you know which peak was which? So I want you to take just a second. I want you to attempt to figure out which is which, and explain why, and then come back. Okay, so this is our helium, 1s, and this is our hydrogen, 1s. And the reason we know that is because helium's peak is going to be twice as high because it has 2 electrons, and hydrogen only has 1 electron. So it's twice the height. So helium's peak twice as high. Because it has 2 electrons. Okay, so which element has a greater attractive force for its electrons? Is it helium or is it hydrogen? Well, it's helium. So helium, and that's because it has more protons in its nucleus. Because it has more protons in the nucleus. Okay. So next one, we're going to read our graph. So helium's binding energy is about how many megajoules per mole? Let's see. So if I look about here, it's between 2 and 2.5, roughly here. I'm going to call that 2.3-ish. So we'll say it's about 2.3. And hydrogen's binding energy right at the top of the peak, right there, I'd say it's about 1.3. And if we look at the actual numbers in published data, helium's actually 2.37, which we couldn't really tell from here. And helium is actually 1.31. So, but this is close enough. Now let's go ahead and consider lithium. So Z equals 3. Right here, atomic number 3, lithium. It's got 3 electrons, 3 protons. Write the electron configuration for lithium. That one's pretty simple. 1s2, 2s1. Now let's consider the 1s peak for lithium. So for the 1s peak for lithium, the electrons in lithium's 1s orbital will feel a weaker or stronger attraction to the electrons than the electrons in helium's 1s orbital. Well, think about it. Remember, lithium has 3 protons. Helium has 2. So that means that lithium is going to attract its electrons stronger than helium does. The peak height, however, will match that of, is it helium or hydrogen? Well, if we think about it, if we're looking at just the 1s, it's 1s2, so it's 2 electrons. That should be the same as helium over here because there's 2 electrons as well, so it should match that of helium. And then we're going to sketch lithium's 1s peak on the spectrum above. All right, so if I know it's more attracted to the nucleus and the peak height's the same, I'm going to need to draw it somewhere over here where it's closer to the nucleus, more attracted. It doesn't really matter where you pick, as long as it's over on this side somewhere. So you also want to make sure that this peak height is going to match, because we want to make sure that we show that we have 2 electrons, just like we did in helium's 1s orbital. So this one is going to be lithium 1s. Okay, taking what we did on the 1s peak, I'd like you to please pause the video and consider the 2s peak for lithium. Go ahead. Okay, so the distance, or d, for the 2s orbital is going to be greater, so it's farther away. So the distance is greater than any of the 1s orbitals. Therefore, the force of attraction and binding energy is going to be less because it's farther away, right? And so the farther away it gets, the less it's attracted to the nucleus and the binding energy of any of the 1s orbitals. And the 2s peak height is going to match that of hydrogen because there's only 1 electron in there. And so we're going to go ahead and sketch that on the spectrum above. So we know it's less attracted than any of these other orbitals. So we're going to draw it somewhere over to this side. Doesn't really matter where you draw it as long as you show it's over to this side. So I'm going to pick right there. And so that's my lithium 2s. Make sure you draw the peak height the same as hydrogen there to show that there's only 1 electron in lithium's 2s shell. Okay, so that is it for lesson 8.2. See you soon for the next lesson. Bye, everybody.